at GSK next week. So that'll be my final interview, and I'll make a decision then.
So just by way of procedure, Courtney's going to give us a presentation. After that, we can have questions from anybody who's here. And then we'll ask the guests to leave, and the committee and Courtney will have a little bit of a fight, but with the door closed. And then Courtney will leave, we'll discuss, you'll come back, and you're done.
Okay.
Can we do that in a half hour?
No.
So why don't we start?
Okay, great. All right, so thank you all for being here, first of all. I really appreciate it. Today I'm going to present to you my dissertation research, which is all about statistical approaches for determining the future design and analysis of calcium-41 clinical trials to study osteoporosis. So first, a little bit about myself and my background and interest. So my research and career interests, I mentioned earlier, are very much focused in biostatistics. So how I like to approach statistics is, given a problem in an applied health field or a biomedical field, how can I apply my tools to come up with a solution to the problem? So you'll see that theme carried throughout my own research. Here I list some awards and then also some teaching opportunities I've held while here at Purdue. I also list some presentations and then publications, making note of this first publication I'm very excited about, which is my first primary author publication, which is now under review at Statistics in Medicine. Okay. So here I'll start with some motivation and introduction behind the research problem. Then I'll go into my first research contribution, which is all about the modeling procedure. The second research contribution, which deals with the simulation study, and then finally some wrap up and conclusion. So this research primarily focuses on postmenopausal osteoporosis. So of the 10 million Americans with osteoporosis, women represent 8 million of them. So why is it that women are disproportionately affected by this disease? Well, once a woman reaches menopause, there's a significant drop or decline in the amount of hormonal estrogens produced by the ovaries. And we know that estrogen is very important for building strong and healthy bones. So actually up to 20% of bone loss happens in the first 5 to 7 years after menopause. So the result is low bone mass, which then can lead to a high fracture risk. And we know high fracture risk is a major public health concern due to the fact that it can cause long-term disability, poor quality of life, and in some cases, even death. So then, in an effort to combat postmenopausal osteoporosis, the Women's Health Initiative was initiated by NIH in 1991 to address the major causes of morbidity and mortality in postmenopausal women. So this was, and one of those being osteoporosis. So this was a national health study of postmenopausal women, and they came up with these prevention strategies for osteoporotic fractures. So these a set of those prevention strategies was these hormone therapy randomized controlled trials. So there were 3 arms here. There was an estrogen arm, an estrogen plus progesterone arm, which is another female hormone, and a placebo arm. And these trials went on average for about 5 years until they were stopped, unfortunately, by the DSMB, the Data Safety and Monitoring Board, who found that these women were at increased risk of negative health outcomes, such as breast cancer, stroke, and cardiovascular disease. So then, in response to the Women's Health Initiative, more women are seeking alternative medicine. This just describes non-mainstream healthcare approaches or practices. So our research group focuses on these. There are many forms of alternative medicine, and our research group focuses on these biologically based approaches. So these are your dietary and natural products, things like herbs, vitamins, and minerals. And they typically come in the form of dietary supplements. So our research group looks at assessing these treatments for their potential positive effect on bone. So we've looked at dietary natural products such as soluble corn fiber, which is found in a lot of foods and beverages, hesperidin, which is a compound found in citrus fruits, and there's a blueberry study that's going on now, which is under the sample analysis stage, looking at different doses of blueberry and their effect on bone. So the great thing about this alternative medicine is that it is safer and perceived more tolerable than its pharmacologic counterparts, which is the estrogen therapy. So now I want to get into how we assess these treatments, or how we start to talk about bone calcium metabolism. So, and this deals with the title at the top, so very important. This is calcium-41 technology. So first of all, calcium-41 is a biological tracer of bone resorption. So what happens is these women will say, are dosed with the tracer, so 1 intravenous bolus dose of the tracer, and they're allowed about 150 to 250 days for that tracer to clear from blood, clear from soft tissue, and establish stabilization in the system. So we call this the equilibration period. So it's known that after this period, any excreted tracer represents or is a proxy for bone calcium metabolism or net bone turnover. So essentially, the difference between calcium 41 being released from the bone by bone resorption and then reincorporating to the bone by bone accretion. So it's this net effect that's going on. So what we get out from these studies is this urinary ratio of calcium 41 to total calcium, and that's measured by accelerator mass spectrometry. And you see the accelerator here pictured in the background. So what that accelerator does, it actually counts or quantifies the number of calcium 41 atoms present in a sample, in our case in a sample of urine. So smaller ratios indicate a more positive effect of treatment. So essentially less calcium 41 being excreted, more housed in the bone. And what's unique about this technology is that it is sensitive and rapidly responding. And that's in contrast to some other popular methods for measuring bone calcium metabolism like DEXA, which can take anywhere from 6 months to 2 years to detect any significant changes in bone. Okay, so next here, I'll get into my first research contribution, which is all about the modeling procedure. So here is the urinary excretion curve, the calcium 41 urinary excretion curve. On the x-axis here, we have time, and that's post-calcium 41 dose. And on the y-axis, we have the ratio, calcium 41 to total calcium. And you see this curve is decreasing over time, particularly in this equilibration period. You have rapid excretion, and then here in the post-equilibration, you see more of a steady state behavior. So our goal here is to come up with a statistical model for this curve. So this curve characterizes calcium 41 urinary excretion in the absence of treatment. And what's important about this curve is that it provides a fixed index to where we can accurately quantify treatment effects. So any kind of perturbations from this curve are indicative of the magnitude of a treatment effect. And these curves are subject specific and sometimes even called subject profiles. So every subject has associated with it its own urinary excretion curve. So the research aim here is to create this formal or standard approach to make sure that how we handle calcium 41 data and how we analyze calcium 41 data is consistent among the clinical research community. So more specific, the first aim here is we want a model that's going to accurately quantify treatment effects. We want that model to fit the biological theory and also be simple enough to analyze statistically. We also want to assess the protocol for the equilibration period. So currently, backed by the literature, the equilibration period is defined as 150 to 250 days post-dose. So we want to be able to assess this going forward to determine if any critical revisions are necessary. And then we can also establish equilibration or determine equilibration in other subpopulations of interest, such as premenopausal women, for instance. So in review of the literature, initial mathematical or statistical models for bone-seeking tracers such as calcium 41 sought simple, more computationally tractable models. So this is the use of standard mathematical functions, such as power functions. And calcium 41 excretion can be conceptualized in terms of a compartmental approach, where model terms correspond to specific calcium 41 pathways. Biological theory suggests that these pathways are dominant at different time periods. So initially, calcium 41 excretion dominates in the equilibration period from soft tissues. And then in the post-equilibration period, you have excretion from bone, both trabecular and cortical bone. So here are some initial models that have been used for the calcium 41 excretion curve. So the response variable here is our ratio, calcium 41, and then our units are time here, our explanatory variable. And the parameters A, B, C, and D reflect individual subject differences in urinary tracer excretion. So Dink's model here is this combined exponential power model. So you see this first term here is intended to dominate in the equilibration period, so that should be excretion from soft tissues. And then the second power term here should represent excretion from bone, making no distinction between cortical and trabecular, just general bone turnover. Nolan's model here uses a combined exponential linear model. And Nolan's model, I should mention, focused primarily on the only focus on the post-equilibration period. So here he uses this first term to represent excretion from trabecular bone, and then this linear term here to represent excretion from cortical bone. So only looking at the post-equilibration period. And then my model I propose going forward is this spline power exponential model. So you see that my model here uses similar terms, but the distinction is I confine these terms to the time periods in which they correspond. So taking full advantage of their dominant behavior. So the other distinction of my model is, that it avoids many of the deficiencies of some of the other models, or these other two models. So in Nolan's model, the main deficiency is that he only looked at the post-equilibration period, modeling that period, and not the full curve, which is what we want. In Dink's model, this was more of a biological deficiency. So this first term here, which should represent excretion from soft tissues, is intended to dominate in the equilibration period and then become negligible in the post-equilibration period. But we found with using data from our own studies that this first term was actually still pretty influential in the post-equilibration period. Okay. So before I actually get into the modeling steps, I just want to remind you of the goal here, and that's to make sure that we have this formal or standard approach to ensure that we're consistent in how we analyze this data and how we handle this data. So I packaged that in terms of a modeling procedure. So a step-by-step procedure to ensure that we have that consistency. So this, here I'm using this working example of isoflavones for promoting calcium absorption and preventing bone loss in postmenopausal women. So isoflavones are a class of phytoestrogens, and they're plant compounds that have a similar structure to estrogen, and they're found in soy plants. So that would be your alternative medicine there. So this study had 23 healthy postmenopausal women. There were 5 treatments. It was a 2.5-year double-blinded randomized crossover study. And 150 days was used, about 150 days was used for the equilibration period for all of these women here. So here I just show one example, here I show the data for just one ID. You have observations in your equilibration period, noted by this E, and then you have these observations here in your post-equilibration period. So B here representing baseline observations, and then you have all of your washout or control observations. Next, step 2 here is data handling, or the data cleaning rules. So these rules were established either to avoid model convergence issues or improve model fit, or how these rules were established. So the first data cleaning rule is that we need at least one control period post-equilibration, and that's other than baseline. So if we have only one control period there, then we better have at least 5 observations in that period. We'll only model observations about 73 days post-dose. We'll exclude any obvious outliers, and that's just through graphical inspection. We'll also exclude any IDs with a positive slope, as we know calcium-41 should be monotonically decreasing over time. And then if we have multiple, we'll say, output variables or multiple Y values for one X, we'll use the last recorded observation, assuming that is the correct observation going forward. And then we'll exclude all treatment observations as the curve is defined just for, in the absence of treatment. So the response here is the ratio. Our explanatory variable is years post-dose, so you'll see a little later on that we typically use days post-dose, but here we've converted to years as we get more sizable estimates that way. And then the subject identifier here is ID. So here are 4 representative subjects, just arbitrarily chosen to just give you an idea of what the data look like here. So there were 15 subjects total, and that's after the data cleaning. And then here I show the number of observations that we have in each period, in equilibration and also in post-equilibration. In post-equilibration, you have baseline observations, and you also have post-baseline observations. And then finally, you have the total number of observations for each ID. So now we're ready to talk about fitting the actual model, the spline model. So this is a 2-function nonlinear spline model, where the first function here, this power function, represents the excretion from the equilibration period, and then the second function here represents excretion from the post-equilibration period. So our mean response is the ratio. We have time in years post-dose, and this T naught value is the naught value, or sometimes called the join point, and that's typically unknown in the context of the problem, so we'll have to estimate it. And then we have A, B, C, and D, which are subject-specific parameters that reflect individual tracer excretion in each subject. So we have some assumptions that come along with this model. First, we have an additive structure of the response. That's the mean function and the error component. And this is a nonlinear function of unknown parameters. And then we'll assume IID, normal errors with 0 mean. And then PT, as I mentioned before, defines the equilibration, and then ET, the exponential function there, defines post-equilibration. And all model terms here we are non-negative, as we know that calcium-41 curve should be monotonically decreasing over time. So now in order to use this model, we want to make sure that we satisfy this continuity condition, or we impose this condition here. And that's just to make sure our functions connect to form a continuous function and that we have no jumps. So here we can just equate the 2 functions here and solve for one of the parameters. Here I chose to solve for parameter A. And we see in solving for one of the parameters, we reduce our parameter space by 1. And now we can go ahead, and so we have the reparameterized model, and we can go ahead with the nonlinear regression steps. So going forward here, you'll see that I used SAS nonlinear procedures to fit this model. So the first thing I'll do here for this to fit the model is I'll obtain initial values for what I call those core parameters, B, C, and D. And then once I have those, I want to estimate a neighborhood for T0. So I'll first treat that as fixed. So I want to give the program some window as to where to search for this parameter. And then finally, I'll fit the model that I'm interested in, which is this 5-parameter model where T0 is now treated as a parameter. So that first step there, we need initial values for those core parameters. So how I'll do that is I'll split the data into equilibration and post-equilibration. So note, and I'm gonna take advantage of the fact that I can linearize this system. So notice here though, I actually combine observations in equilibration and baseline to fit the equilibration period, because if you'll see here in this next slide, we only have just a few observations in this equilibration period, which isn't going to be sufficient to fit a reasonable model. So I go ahead and use observations from baseline here just to get those initial values for that equilibration period. But note also that in doing this, we're still at 250 days post-dose, so we're still in the ballpark of what's defined as equilibration. So then I can fit a simple linear regression model in each period here and get out my initial estimates, and I show those here. And so note here that we only need estimates for B, C, and D as based on the parameterization of the model. Now that we have the core parameters, we need a neighborhood, or kind of telling the program where to search in terms of this T0 parameter. So we'll supply initial values to the 3-parameter model, those core parameters. And then we'll determine a reasonable range for T0 just by graphical inspection. So if you look at the graph here, if you look at these graphs, we want to see kind of where our data split, or where we kind of can define 2 separate functions here. So that's determined to be between 0.3 and 0.7. So with that going forward, I can fit a nonlinear model with each fixed T0 in this range, just in arbitrary increments of 0.05 here under inland. And I want to compare the model sum of squared errors among these different fixed T0 values, these different models, and here I find that the smallest sum of squared errors I get is between 0.4 and 0.6. So I'll use that going forward in terms of this window, or actually called a grid search, for the 5-parameter model. So we'll supply a grid search as before, that 0.4 to 0.6. Here, arbitrary increments again of 0.01, just to get a kind of fine-tuned grid here. And then I'll give a little bit higher upper bound on that T0 parameter just to allow for greater model flexibility. And then I can go ahead and fit the nonlinear model with T0 now as a parameter in inland. And then the last thing I'll have all of my parameters, and the last thing I'll have to do is just solve for that missing parameter A. Lastly, I want to get out information on that missing parameter, and I can't get that directly in inland. So I go ahead and switch over to NL mix, which is another nonlinear procedure in SAS, to get out information on that missing parameter. Information such as statistical information, such as standard error and confidence interval. So I'll take advantage of this estimate statement in NL mix that allows me to get out information about that parameter. So then here I show the actual fits. Once again, the same 4 subjects here. And I can assure you there's 15 total, and I can assure you for the other subjects, we have very similar fit. Here I show the final estimates, and then underneath the standard errors for those estimates. And the other component of model assessment is what I call this homogeneity of variance, or piecewise homogeneity of variance. So what I want to do is I want to make sure that I have equal model fit, or equal error variance in each one of the periods, equilibration and post-equilibration, to avoid any potential bias, particularly if I'm going to do some kind of independent or comparative analysis between periods. So here I'm going to compare the error variance in the equilibration period, that's subscript 1 here, and I'm going to compare that to the post-equilibration period. So I'll use a bootstrap procedure for that. So I'll create B bootstrap samples by resampling subjects. So each subject will have associated with it a mean squared error in the equilibration period and a mean squared error in the post-equilibration period. And then I can compute my test statistic of interest, which is this ratio of mean squared errors. So I can summarize that mean squared errors for each bootstrap sample by this weighted average here of mean squared error. And then finally, I can compute a 95% confidence interval there for the empirical bootstrap distribution. So here we determine We failed to reject the null, and then we conclude that we do have homogeneity of variance in both periods, which is what we like to see. So in summary for this project, the problem is that there's no standard method or procedure to describe the full calcium-41 labeling curve. So my solution is to develop this modeling procedure to be able to describe the curve, to make sure that how we go about doing this in the future, defining this curve and the analysis is consistent among the clinical research community. So my method is to formulate this 5-parameter nonlinear spline model and package it as a step-by-step process. And this is via SAS nonlinear programming analysis. And here I've outlined the steps that I previously detailed. So my recommendation going forward, specifically as it relates to the aims here, the first aim here was model establishment. So to be able to use this curve here and as a reference measure for quantifying treatment effects, for accurately quantifying treatment effects. And the second aim here is more about model application. So I want to be able to assess the current protocol for equilibration, which has been set at 150 to 250 days. So going forward, we want to determine, is this adequate or not? So assuming that this study is a representative study here, you'll see that these women actually require, on average, 186 days for the equilibration period, with a standard deviation of 0.08, and 95% of the women require at most 219 days. So with that going forward, I recommend actually revising the current protocol, and revising that to be at least 250 days, and that's to capture all subjects. So in conclusion, for this project, I have developed this standard or formal approach to make sure how we handle calcium-41 data and how we analyze calcium-41 data is consistent among the clinical research community. Okay. So now I will outline this simulation study, which is my other research contribution. So here we're going to stay within the same context, the same framework, but instead we're going to focus on treatments and treatment effects. So on the x-axis here, we have days, so back to days post-calcium-41 dose. And on the y-axis here, we have the ratio. And you see here, there's this equilibration period. And then we actually start the study here with baseline. This is a crossover study. So you have your treatments in between each washout or control period. This Novasoy 50 is a soy product, so that's your alternative treatment. And this Actonel is the positive control or FDA-approved drug for osteoporosis. So, and then these are 24-hour urinary sample collections. So every data point here represents one urine sample. So then now that we have the data, well, how do we analyze the data? So the first thing that we're going to do is log transform the response to establish linearity. So we know when things are linear here, analysis is definitely going to become a lot more straightforward. So we'll do a linear regression using all the control observations, and that includes baseline. And then in terms of a treatment effect, how we'll calculate that is the average distance. So this is for one subject, the average distance from the control line. So we'll average that within subject, and then we'll average that across subjects. So values below the control line indicate a positive effect of treatment. So less calcium-41 being excreted, meaning more housed in bone. And then when we talk to those in nutrition science or those in the medical field, they are more interested in this percent net calcium retention. So how much more calcium was retained, we'll say, due to Novasoy 50. So essentially, it's the ratio of calcium-41 in treatment as compared to control. And then keep in mind here, we'll use this fact later, that percent excreted and percent retained are inverses or complements of one another, so they'll total to 100. So I'll use that later. Here is the conventional study design, or what I call design factors, for a standard calcium-41 study. So you have 12 subjects, you have 4 control periods, and that includes baseline. We have 3 treatment periods, 5 samples in every period, that's control and treatment, and then samples are collected every 10 days. So under this study design, the total cost of sample analysis is at $168,000, which is pretty substantial. So that's at $400 per sample. So you'll see here that the research aim is going to be to get at that cost. So more specifically, the aim here is to perform a novel simulation study so we can assess the statistical properties of various calcium-41 experimental designs. We seek more efficient, more cost-effective design. So I define design efficiency in terms of maintaining the strong statistical properties of our original design, but significantly reducing the cost. Here's where I show the internal procedures of the simulation. So I will input into the simulation those design factors. And this first step will be to obtain the population parameters for the true control line and error variance. So those true population parameters. And then every observation is just gonna be some kind of perturbation from that true control line. So control observations will have a deviation of just random error, and then treatment observations will also have that same deviation, but they'll also be adjusted by a treatment effect and an associated error for that treatment effect. So then we can proceed with calcium 41 data analysis as normal here, where we estimate the least squares control line. We calculate the mean effect within subjects, so that's calculating those average distances within subject and in between subjects. And then we can get out this pooled standard error of treatment effect. So for every trial, which is defined by these input factors, we will pool across those standard errors for each treatment effect. And then once we run these trials many times, we'll say we run the same trial with these defined design factors, say 500 times or so, we'll get out this summary pooled standard error. So essentially in every one of these designs, these are the three things we'll be comparing. The accuracy of our treatment mean estimates, the detectable effect size, we'll say under 80% power, and then also the cost. So the goal is gonna be to maintain these two, but significantly drop the cost there. So for those of us that are a little bit visual, here I have in tabular form the computation. So you have each trial here, 1 through S. So each trial is defined by this unique combination of design factors. So we're running that same trial several times, or many times. You have subjects here, and then here's the mean treatment effect, that average distance from control line for each treatment. And then we can pool across the treatments to get out this pooled standard error for that trial. Finally, we'll pull across all trials to get out this summary pooled standard error. So that's the measure that we're interested in going forward, one of the measures. So once we obtain the summary pooled standard error, we will input that into a power calculation. So this is under assuming a one sample t-test as we assess these treatments independently and not comparatively. So we'll get out from this power calculation the detectable effect size, that's under 80% power. And so what we can do is back transform that mean effect.
Rebecca's lost yours.
Yeah.
Rebecca wants it to come back awake.
Yeah,
Oh.
no, I got her.
We fixed it.
Yeah, we fixed it.
Oh, we fixed it? Okay, good. She got it. Okay, good. So then we can back transform the mean effect from the log scale. So remembering that the difference of the logs then turns into the log of the ratio. And then we can finally calculate this percent net calcium retention. So we can do a 1 minus here and then multiply by 100 to get out the percent. Remembering that excretion and retention there are inverses of one another. And then we can repeat these steps for each design that we simulate. So essentially we're gonna get out summary pooled standard error from each of these designs and detectable effect size, the effect being the percent net calcium retention under 80% power. So here is the actual model for these simulations. So this is a general linear model, and more specifically a mixed model here. Time is the only fixed effect. We have indices for trial, subject, treatment, sample, and period. And then all of these population parameters are data driven from a former calcium 41 study. And then we've rescaled time from days post-dose to days post-initial observation, just as a normalization measure to get everyone on the same playing field. Here are the model parameters. So what you see here, this time, days is fixed. You have B0 and B1 are your control line intercept and slope. So they are sampled from a bivariate normal. Mu here is your mean intercept and slope. And this sigma here is represents your subject to subject variation, the fact that every subject is defined by their control line. And then Tijk follows a univariate normal. Tau k is the mean treatment effect. And then sigma tau represents your treatment by subject interaction, the fact that every subject responds differently to treatment. And then you have your random error here, which is common to any general linear model.
Can you go back a slide and explain post-initial observation? I didn't get that reading your.
Yeah, so.
Because, you know, some subjects would have many samples through the equilibration and the others, you wouldn't have any and start,
So the first observation for everyone starts at 0. So it's just a rescaling of time.
But,
instead of.
so one of these subjects may be their third study, and another one it's their first study, because the dose of calcium 41 can go for years and years and years.
Oh, right.
So I don't know what you're talking about. Are
In
you talking
terms of-
about this study?
Yes, this particular study, yes.
So it's really not their first post-dose observation. It's
Right,
the
for
first
this
one
study.
in this study, and is it baseline, or it could be before baseline, or?
It's their very first, it would be in the equilibration period, so it's their very first
And if they didn't
observation.
have any samples collected during equilibration, it could be.
They're
the
not
first one on
included.
that.
Well, not for the, So if they don't have, so now we're in a different context. So for the simulation, we're just looking at, we're modeling here post-equilibration. So in the simulation, we're just looking, because here now we're starting to talk about treatment effects, and that's modeled, so the treatments are administered in the post-equilibration period. So we're just here looking at post-equilibration. So everyone's first observation.
So it'd be baseline for that study.
It would be baseline for that study.
Okay,
Right.
now I
Yes,
get it.
Yes, yes, it would be baseline. Okay, so now we have some assumptions here for this model. The first one being that to summarize, our subjects are independent. Here, all our treatment effects are different, they are independent. We have our error terms that are independent, common to a general linear model. And then all of our random effects here, that's assumption 4, are independent. And then lastly, very important here, we assume no period effects, no order effects, and carryover effects. So that's really important for a crossover study. We want to make sure that we highlight this. But I will say under these studies, because we're looking at alternative treatments, they don't tend to have these lasting effects like their pharmacologic counterparts do. So they kind of get in, take an effect, and get out. So we don't tend to have these issues of carryover effects and order effects. So just to remind you of our goal before I get into the results here, the goal here is to determine a combination of design factors that are more efficient than the standard design, what's conventionally been used. So we seek designs which drive down costs, but have a minimal reduction in the inflation of the statistical outcome measures, and that's due to sample reduction. You'll see that in some of the results, So here we want to compare the accuracy of our treatment mean estimates, our detectable effect size in terms of percent net calcium retention, and then compare that to the cost of sample analysis. So here, just remind you of what the standard or conventional design is. It's 12 subjects, you have 4 controls, 3 treatments, you have 5 samples in every period, and then samples are collected every 10 days. So I came up with these guiding questions to get at what that final design choice is going to be, just so we're not going about this blindly, but we have some direction in terms of what that final design choice should be. So the first question is, which type of samples, whether it be control or treatment, should be targeted for sample reduction? So here you'll see similar tables in all the results. So this first column here represents the number of samples, whether it be in control or treatment per period. You also have this plus here, which represents the percent increase in the statistical outcome measures. So for instance, if we look in this first row here, this says that we have 4 and if we look under control periods, this says we have if we have 4 samples per control period, we're going to increase those statistical outcome measures by about 1%. And you see all these are increases due to the sample reduction, as a consequence of sample reduction. So in determining, should we target treatment samples or should we target control samples for sample reduction here, I determined here that's actually going to be much more efficient, that's the double arrows there, to target control versus treatment. So much more efficient in the sense that you more than double your percent increases when you look at eliminating from treatment versus control. And there's also get more bang for your buck in the sense that there are more control periods than there are treatment periods. So essentially that's a greater cost reduction. So for this here, I'll decide target control samples for sample reduction. The second question, where in the study timeline, so now that we've decided to focus on control, should samples be targeted for sample reduction? So either I will define either the middle controls, which are controls 2 and 3, or 1 and 4, which are the outer control periods. So similar table here, and actually a similar result, that it's going to be much more efficient here to eliminate from the middle controls than it is from the end controls. The end controls more than double, again, those percent increases in those statistical outcome measures. So then here, the decision is to target the middle control samples for sample reduction. The next question I thought to be the most interesting, can we reduce the number of days between sample collection? So Rogers and colleagues used a 7-day sample collection for this calcium 41 study. So we thought to look into that. So that choice is actually attractive for several reasons. So first, you have reduced subject burden. So the study goes from 360 days to 238 days, so 3.5 months that have been reduced. You also have reduced logistical costs, the amount of drug that needs to be purchased, also the cost of labor. And then lastly, you have potential for increased subject compliance. So a 7-day sample collection is certainly more natural than a 10-day collection. So telling these women, I need for you to collect your urine weekly versus every week and a half might help them to remember that more. But I will say in these studies, subject compliance does very well. Okay. So here looking at the 7-day versus 10-day here, determined that that 7-day, double arrows here, once again signifying is going to be much more efficient in the fact that you have greater increases here under the 10-day, but much more efficient in the sense that we have those practical advantages that come along with the 7-day and also the cost advantages that come along with the 7-day. So here we determine reduce to the 7 days between sample collection. And then this last question, what is the trade-off between the number of study subjects and the number of samples per study subject? So is it going to be more efficient to have more subjects and less samples per subject, or less subjects and more samples per subject? I got that right. So this is what I call integrating the design factor. So this is now bringing everything together, not just looking at things independently, so now bringing it all together. You have 7 different design schemes, so these were chosen from the viewpoint of the clinical study investigator. And then we have control allocations, the number of control observations per control period, remembering that we decided to leave treatment alone. Total number of samples per subject, total number of subjects, and then this very important column here, the analytical cost recovered. So essentially this is the difference between the original cost, the $168,000, and then the new cost. This is at $400 per sample. And then we get out here the statistical outcome measures from these designs. And you see even in some designs, we're actually improving upon those measures. So getting back at the question of more subjects, less samples per subject, or vice versa, I chose here 2 different design schemes to try to answer that question. So you'll see in design scheme 2, there are less subjects, 12 versus 14 here, but more samples per subject, the 31 versus the 27. So in design scheme 2, you have greater cost savings, but less statistical validity. In design scheme 6, you have less savings here, but greater statistical validity. So we determine here this question is actually inconclusive, that it's really a much broader question at play. And that question is the substantial improvement in the statistical outcome measures, design scheme 6, worth the decrease in recovered costs. So that's the broader question. And that's certainly a question to be had between all those involved in the study, the clinical study investigators, certainly the statistician as well, to determine an answer to that question. And then also I should mention that it's not always the case that less subjects and more samples per subject implies a greater savings and less statistical validity, which further makes this question inconclusive. So it's really about location, sample, control allocation and location of these samples that matters. Okay. So in going forward, I want to recommend a new design here, and using cost as the main driver, keeping that in mind as that was the original aim here of this research, I recommend here design scheme 3 going forward. So that design removes 96 total samples from the study. That's at 8 samples per subject. And this design is more efficient than the original design in terms of the fact that we've maintained the strong statistical properties of the original design in terms of standard error and power, but that cost factor has been greatly reduced. So over $38,000 in recovered costs, which is pretty substantial. So the problem here for this research study is that these calcium-41 experiments are very costly, particularly sample prep and analysis. So my solution is to perform this novel simulation study so we can analyze different experimental designs. So I assess the accuracy of the reported mean estimates, the power of the study to detect given effect sizes, and also the cost here in response to these following design factors. So my recommendation going forward is a 7-day design scheme, retaining 12 subjects here, also retaining the number of periods that we have. We also have still five treatment samples. That was based on that one of the first guiding question. But here, 2 samples in the middle controls now, and 4 samples in those end controls. So that total gives us 27 samples per subject. So in terms of design efficiency, over $38,000 in recovered costs under this design. We have even greater cost reduction due to the fact that that study time period has been reduced by 3.5 months. And then the whole goal here is that we maintain the strong statistical properties of the standard or conventional design. So in conclusion for this project, the great thing about the simulation is that we have the ability to assess many different design schemes when conducting these in person is not financially feasible or practical. Okay, so now I'll give some wrap up and conclusion. So at the intersection of both of these, kind of bringing both of these research pieces together, is my goal here is to create these tools, these statistical tools that can be implemented or integrated in the clinical research community. And I'm hoping that will promote the widespread access and utility of calcium-41 technology and clinical experimentation. So this simulation study gets, and then essentially, hopefully that will lead to novel treatments in osteoporosis prevention. So the simulation study gets at that goal by increasing the cost effectiveness for the practicality and the financial feasibility of these studies. And then the modeling procedure helps that goal by promoting the uniformity and transparency in how we handle the data and how we analyze the data. In terms of future work, so for the modeling procedure, there's a premenopausal study that's going on now. That's now in the sample analysis phase. So we want to be able to determine an equilibration time period for that group, as calcium-41 has not been studied in premenopausal women. So we also want to compare that equilibration period to postmenopausal women as well. So the hypothesis being that postmenopausal women might require a shorter equilibration period, possibly due to metabolism or diet and lifestyle factors. And then we also want to establish equilibration for other subpopulations of interest, such as adolescents or even males. And in the simulation study, future work would be first making this more user-friendly, more user accessible. So that would involve making the program more efficient. So right now things are very much brute force, but an automation of design specifications would certainly help. A point-and-click system or some kind of GUI, graphical user interface. We can certainly look at additional designs. So if you notice here, there were only 7 design schemes here that were analyzed. There's certainly a countless number of different design schemes that we can look at. We can also look at making this approach more rigorous. So defining this in terms of an optimization approach, where we might minimize some cost function. And then we can also look at more than 5 samples per period, as 5 was the cap here. And then lastly, we can look at extending this simulation to other subgroups of interest, such as premenopausal women and even in preclinical studies. And then so looking forward in terms of the future of calcium-41 technology, which the future looks very bright for this technology, there's been an increase in programs devoted to biomedical accelerator mass spectrometry. There's also been an increase in commercial AMS facilities, both used by pharma and biotech companies. There's a new generation of AMS instruments, which are at a lower cost than their tabletop instruments. So that's going to help to promote the financial feasibility and practicality of this technology as well. And then there are these forthcoming studies here at Purdue Prime Lab. The Blueberry study and the birth control study, which are now in the sample analysis phase. The premenopausal women here in the birth control study, so that'll be the first of its kind in that group. And a very interesting study that's in the works now is this Plum and sex steroid study looking at hormone deficient women and men. So this will be the first calcium-41 study in men. And then lastly, here, there's been recent research that's come out about this natural calcium isotope, which would replace the calcium-41 isotope. So essentially the advantage there is that we wouldn't have an equilibration period. So we wouldn't have to dose the women, and we certainly wouldn't have to wait that 150 to 250 days to actually start the study. Okay. So acknowledgements here, I certainly want to acknowledge Dr. McCabe here and Dr. Weaver here for many years of guidance and mentorship and training. Also Professor Craig and Professor Minzang for agreeing to be on my committee and also your support as well. My collaborators here, Berdine Martin, Linda McCabe, George Jackson, and Monroe Peacock. So as you see, this research is very highly interdisciplinary and very collaborative, which is what I love about this type of research. And then I also want to acknowledge my research support through NIH, the National Center for Complementary and Integrative Health. And then my Purdue family, I want to thank you guys. I couldn't do this without you. Professor George, thank you so much. I owe you my life. I thank you so much for being here and sharing this day with me. And then here's the conclusion there. Thank you guys.
Questions?
You did a great job. So I have a question about the rescale time.
Mm-hmm.
Can you talk about that a little bit? I didn't really.
The same. So here we rescale time in the sense that we take, just as I said, kind of as a normalization measure. We get everybody, so everyone's initial observation, we'll say, starts at 0. So as the time increments there, everyone will, so starting at 0, as I said, kind of is that normalization measure to kind of get everyone on the same playing field. So it's really just starting the time at 0. So everyone's first observation will start at 0. And then we'll say 10 days later, the time will be 10 and so on.
Okay, so how do you think that affects like
So I'm not sure, so it's really just shifting, I think we're just shifting necessarily the x-axis, so I don't think we're changing per se anything, we're really just kind of making a shift over, so everyone starts at the same time, the 0 time. So I don't believe that it would to change analysis
Okay,
at all.
and is this like retrospective then?
No, so this is prospective data, so this is longitudinal
Okay.
study, yes.
Okay.
In your first part, you mentioned the spline model, and the simulation study was based on the linear mix model after log transformation.
Right.
And I understand maybe after the
Equilibration.
equilibration,
Yeah.
thank you. After that period, the linear pattern is more obvious or stronger, but
Yes.
have you considered comparing the two parts, like spline model in the power calculation or power calculation results and use the spline model to fit the treatment impact?
Use the spline model to,
Use the spline model to impact the treatment effect from your simulation.
yes, so with the spline model, notice that spline model fits the whole curve here. And so we're saying so for the simulation here, remember treatments don't start until post-equilibration. So we're essentially fitting that second half there. And that second half from the modeling procedure, I've defined as an exponential function. So essentially we linearize that function there. Does that make sense? Okay.
Thank you.
Yes.
I have a question.
Yes.
If I'm not incorrect, so you said that you would reduce the amount of samples for the controls in the middle to 2 samples, right?
Yes.
What time in that control period would you suggest taking those samples? Like closer to the end of the treatment period when the bodies were washed out of the treatment, or in the middle?
Mm-hmm. It was interesting. We actually looked at with the simulation. So when I talk about 4 samples per control or 3 samples per control, if it mattered which samples I was eliminating. So we actually found though in the simulation that we got very similar results no matter if we took within that period, 2 from the ends or 2 from the middles. But that didn't quite go along with what I was initially thinking. But based on the simulation results, it really was not much of a difference on where I eliminated within that period. Brianne?
Great presentation,
Thank
Dr. Heck. I have a quick question regarding the biological theory. So it's clear that you need the equilibration period for the calcium 41 tracer to pass through the soft tissue phase and stabilize the bone. But can you explain maybe why the 2 different types of bone, trabecular and cortical, might be modeled separately?
Yeah, sure, that's a good question. So in Nolan's model, right, he modeled those two terms separately. So the trabecular bone is more of your your faster turnover for trabecular bone and slower turnover for the cortical bone. So in Nolan's model, he had data, I think, like 600 days plus dosing. So he was able to say that way out in time, once you start getting, when we get excretion from that cortical bone, that's modeled around that time period. So way out in time. So post, I said maybe 600 days or so post-dose. But for our study, or particularly for these type of studies, we typically don't have that long of a time period. So that general bone turnover term was sufficient for this model. We didn't have to distinguish between trabecular and cortical.
Anything else? Well, thank you for answering those questions.
Okay.
So we'll just meet with the